Hey there, and welcome to all again. We're going to be doing using TASA structure. This is what I refer to in the syllabus, an introduction to structural methods. I'm going to be playing this. Forgive me for the sound. I'm not exactly sure what the issue is, but it does crackle here and there. But I think you can hear it. If you can't hear it, you guys read all the words because all the words that are there, they speak. I'll be adding some things here and there. I'll try to keep that to a minimum, but sometimes I just can't help myself. So with that said, why don't we get started? We're going to be talking about elements of lines and planes today. Now in structural methods, when we're mapping and using structural geology, we are measuring lines and we are measuring planes. We're doing this in the field with the Brunt and compass. So let's introduce you to a little bit about those methods. And it ties into the lab that we're doing this week on lines and planes.
Structural geology, many topics of interest involve relationships between lines and planes. In order to work with these geometric objects, we need to specify their orientations in space. These large grooves on the surface of a normal fault are formed by drag and provide the direction of movement or net slip, red line, during faulting. These sub-horizontal linear columns are developed in a granite mylonite near Akayaka, Sweden. This elongation lineation is parallel to the transport direction of large sheet-like rock masses. These fold mullions, red lines, are developed in the hinge region of an anticline and parallel the anticline's hinge line. Symmetrical ripples, the red lines, on a bedding plane provide information about current direction as the current flows, the blue line, at right angles to the ripple crests. Well-developed bedding planes are nicely illustrated in this exposure of old red sandstone. Important geometrical elements of this chevron fold can be determined from the intersections of the fold's planar limbs. Yellow lines indicate the edges of planes parallel to the folded beds. The geometry of this synform can be represented by a few planar segments. Note there is another subtle yet pervasive planar feature that parallels the bisector of the fold.
So if we follow the yellow lines, we can find those planes with a set of measurements, and that helps us to define the fold. The bisector of a fold is just a center line that cuts the fold in half. The parallel lines on both sides, these are, again, lines that we can take measurements of and report that back on describing this fold.
Complex fold shape and minor faulting in sandstones near Efford Ditch, North Cornwall, UK. Fold geometry can be represented by a number of planar segments. The traces of these planes on the cliff are shown as yellow lines. To determine the orientation of a line in space, it is necessary to specify a horizontal and a vertical angle for that line. Once you have learned to do this, determining the orientation of a plane is straightforward, as you need only measure the orientation of two lines within that plane. The orientation, the limb of the syncline in the photograph, can be defined by measuring the orientation of the yellow lines in the plane of each limb.
So these measurements, you see marked out in yellow, helps us define the planes of the fold limbs, And these fold limbs are what we would measure and what we would bring back and we would plot on a geologic map, or if we were creating a map. We can see the fold back here in the background.
In the diagram on the left, the yellow line is contained in a vertical plane. There is only one vertical plane that contains this line, and therefore only one vertical angle associated with the line. Inclination is the general term used for an acute vertical angle measured downward from the horizontal. Geologists normally use the term plunge when referring to the inclination of a line.
Okay, this key word that you need to know, plunge. Plunge is the inclination of a line. This is the other key piece, line. What we're looking at is this yellow line. This is the horizontal surface, and usually in structural geology, we use the Earth's surface as a horizontal surface, and we can measure an acute angle to determine the plunge or inclination of that line. Again, we're going to be looking at this in a little bit. It'll be hopefully a little bit more straightforward as we move through this discussion.
The vertical projection of the yellow line on a horizontal plane, the dashed line, is the same as the line of intersection of a horizontal plane and the vertical plane containing the yellow line. The horizontal angle is measured using this projection.
Okay, this is a little complex, and I'm not going to spend a lot of time with this. However, in a future lab, we're going to be looking at vertical projections and basically learning how to read 3 dimensions in a 2-dimensional object. Basically what we do when we look at a structural or a geologic map.
The trend of a line is its compass direction in a horizontal plane, its horizontal angle measured with reference to geographic north. 2 conventions are used to specify trend: bearing and azimuth. Note, if you haven't already, that you can repeat the animation by clicking on the yellow eye beneath the diagram. Bearing specifies the trend of a line by denoting its position in degrees east or west from north or south.
Okay, so again, this is just reading a compass. Each one of these lines basically is representing a bearing. And so north 80 degrees east, we just come down here 10, 20, 30, 40, 50, 60, 70, 80 degrees. That gives us a direction. I'm hoping that most of you have some experience in reading a compass. North 20 west, south 30 east, south 75 west. This is what we often do in just reading a compass in everyday life. This isn't quite what we do in structural geology or as geologists. And we're going to learn how to do that, what we do as geologists as we move forward.
In order to test your understanding, identify the bearing of each arrow by dragging the correct direction to within the box by the appropriate arrow.
Okay, so let's look at the first one here. What do we think? If this is north, and each one of these lines is 10 degrees, and this is east, this would be north, 10, 20, east. So I'll just bring that up there. Go ahead and take a look, take a few seconds to look at it. Then I'll go ahead and put in the rest of them. What do you think? Do 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 do. Oh, forgive me. I get caught up in all the fun of this. So, what do we think? This is to the southeast at about 10, 20, 30, 45 degrees. So that's south 45 east. This is 10, 20, 30, 40, 50, north 50 west. South 10 west, and is this right? There you go. I hope that all of you got that. If not, sit here for a little bit, back up your video, take a look at it a little bit more and go through it again. You did not quite understand.
Azimuth specifies the trend of a line by denoting its position in degrees clockwise from north, or 0, 0, 0.
So in this case, we're not using northeast, northwest, southwest, so forth. We're just using the azimuth degrees. So if I were to pick 10 degrees here, it would just be 0, 10. We know 0, 10 is to the northeast. 150, we just write down 150, we know it's to the southeast. 340, we write down 340, we know that's to the northwest.
In order to test your understanding, identify the azimuth of each arrow by dragging the correct direction to within the box by the appropriate arrow.
Okay, so I'll look at it again. Here's the first one. We're at 0 degrees north. It measures 90, 180, 270, backed up to 360. We know this is 10, 20, so we drag 0 to 0. Go ahead and take a look at it for a few seconds before I fill in the others. See if you can figure out what they would be. I won't sing this time. Well, technically I am. It's going in my head, but you don't have to hear it. Okay, so what do we think? This is 90, 100, 20, 110, 120, 130. That's 135. It helps if I can count. 180, 190, 310. And you can check it, is it right? There you go. Again, take a look at it, go backwards, watch it again if you don't quite get it first time.
The orientation of a line is completely defined by specifying its plunge and trend bearing or azimuth. Most geologists use plunge to refer to the inclination of a line. The trend is measured in the direction in which the line plunges downward into the subsurface. This convention is used because geologists normally are interested in materials that are located beneath the Earth's surface.
Okay, so when we're looking at this, this is our line. And if I was standing here on the Earth's surface, I take my compass and I would measure in the direction of the line. Let's just pretend for the moment that that's directly to the west. So we would say that's, if we're using an azimuth method, that would be 270 if it's directly west. It would be 270 degrees. The plunge is this acute angle. So this line now, as I'm measuring, is plunging down into the Earth's surface at some angle. I can use my compass, my Brunton compass, and we're going to see that in a little bit with a clinometer. I can measure that angle, and then I can record the plunge and the trend.
By convention, when writing the orientation of a line, plunge is listed first, followed by the trend. The notation is 36 north 70 east if using plunge bearing, and 36070 if using plunge azimuth. In order to avoid confusion when employing azimuths, always use 3 digits for the azimuth.
Okay, so what I want you to remember here, and you need to write this down, put someplace in your memory, tattoo it on your hand. By convention, when writing the orientation of a line, plunge is listed first. So this angle of inclination is always first, followed by the trend or the direction of the line. So in this case, we're using a quadrant method or a bearing method. So we have a plunge of 36 degrees north 70 east. If we use the azimuth method, we have the same plunge angle, 36 degrees, but now we're just recording azimuth as 070. Key thing is the azimuth is always reported in 3 digits. If it's less than 100, you have to put a 0 in here. That way you don't confuse this number, the azimuth direction, with the plunge. This plunge is always 90 degrees or less. So it's 90 to 0 degrees. So this can go up to 359 degrees. But we want to make sure there's a 0 in there, so we always read that correctly. But remember, plunge angle is first, followed by the trend. Write that down.
Horizontal lines, of course, have no plunge, and normally it makes no difference which end of the horizontal line you use to specify trend. Vertical lines plunge 90 degrees and have no trend. A line's orientation is portrayed on a map by drawing an arrow with the correct trend and placing the plunge at the arrow's tip. Be sure you could draw the arrows as shown from the orientations given, or vice versa.
Okay, again, the horizontal lines have no plunge. They just have a trend. Vertical lines are 90 degrees plunge and have no trend. This is the symbol for a linear or line feature. When we're talking about a linear or a line feature, we use this arrow pointing in the direction of the trend. So if I were to put compass around this, 0 being straight up, 180 being down here, this is 200 degrees, and we put the angle of plunge at the end, 36. This will be placed on a geological map. If I, as a geologist, when I look at this, I know direction of plunge and I know the angle of plunge. Same thing over here, other than the fact this one is plunging toward the northwest, in this case 350 degrees, or north 10 west, at an angle of 15 degrees. Again, write these down and practice. We are going to be doing this in lab.
Geologists normally measure horizontal and vertical angles in the field using a Brunton compass, or a compass with a design much like the Brunton.
So this is our Brunton compass. There's a video that talks about how to make measurements with a Brunton compass that you can watch, and there's some information in the lecture as well.
To read a horizontal angle relative to geographic north, a geologist uses the sighting arm, bullseye level, graduated circle, and compass needle. To read a vertical angle, geologists use clinometer level, the clinometer scale, and the vernier, which is attached to and moves with the clinometer level. To measure the trend of a line, you hold the Brunton level using the bullseye level as a guide and align the axis of the compass and the sighting arm parallel to the line and in the direction of plunge. Trend is then the reading on the graduated circle at which the north-seeking end compass needle is pointing.
I'm hoping that's fairly straightforward. Basically, we're looking at the compass face. We're getting the direction in which the line is trending. And then, of course, from that, we can then measure the plunge.
To determine the plunge of a line, place the compass on its side and parallel to the line of interest. Be sure the plane of the compass is vertical as you are reading a vertical angle. Then, center the clinometer level by moving the lever on the back of the compass. Read the plunge angle on the clinometer scale at the position across from the 0 point on the vernier. Check the boxes that correctly express the orientation of the yellow line.
Here's our compass. North is this direction. So from that, we should be able to tell that we are going in a northwest direction. Our line, our trend of our line is to the northwest. We have to guesstimate an angle here. They've given us what appears to be a couple choices, 55 degrees or 35 degrees. And it's asking us to check the boxes that correctly illustrate the trend and plunge of this line. So this looks like it's closer to 55 degrees. This is to the northwest. Remember, based on by convention, north is up. So if we had a north arrow here, north is up, so that would be to the northwest. So I'm going to choose that one. And based on where I'm looking at it going in terms of the compass, I'm going to choose this one. Okay, we did again. And again, go back through this, repeat the video, watch it again if you're confused on what we just did.
Any plane contains an infinite number of lines, and one of these lines has a greater inclination, vertical angle, than any of the others. If the orientation, plunge, trend of this line of greatest inclination is known, the plane in which it lies is completely and uniquely defined.
Okay, this is a little bit confusing, but basically what we're seeing here is this is the surface of the Earth. So this is the horizontal surface. This is a unit this is the plane that's inclining into subsurface. And what they're stating is if we draw a series of lines, we can draw line after line after line that cross someplace in the center of this plane. But there's only one line that has the greatest acute angle that intersects the horizontal. That's this line right here.
This line of greatest inclination in a plane is referred to as the dip line, and its inclination, and hence the inclination of the plane, is termed the dip. Horizontal planes have no inclination and therefore contain no dip line.
Okay, so this line is perpendicular, 90 degrees to this line. The dip of a plane that we're measuring is always 90 degrees. We want to find that 90-degree angle to get the maximum inclination of that plane. As it states, horizontal planes, which would be if we just had a surface and a plane coming out there, horizontal planes have no inclination. Therefore, they can't have a dip. So, or you can think of it as having a zero angle of dip.
In an inclined plane, a line drawn perpendicular to the dip line will be horizontal. This horizontal line in a plane is referred to as a strike line, and its trend, azimuth or bearing, is called the strike of the plane. In practice, many geologists first locate the strike line because it usually is easier to determine, which then fixes the position of the dip line.
So again, we're looking at the same plane. Here's the horizontal surface of the Earth. If this was a rock outcropping at the surface, we would stand here and we would measure the strike along that line, which is your strike line. This would be an azimuth or bearing. In other words, it could be something like north 45 degree east or 045. And then from that at 90 degrees, we then measure the dip angle. The dip angle. If we know the strike direction, we don't have to measure the dip direction. It's given. But we do have to measure the dip angle.
In order to help visualize the position of the dip line and strike line on a plane, you can rotate this block with the mouse. Note the yellow hand symbol in the lower right of the diagram. Such a symbol alerts you to the fact that the diagram can be rotated by holding down the mouse button and moving the mouse.
So we can rotate this and we can take a look at it from a little bit from the side. Maybe that's a little bit easier to see. So if you're standing right here, you can see there's a nice line that's created by the intersection of our dip plane and the horizontal surface of the Earth. We can measure that direction with our compass. And of course, then we have the angle, the inclination. And we can measure that inclination, which is the angle between this horizontal plane. Bring it out here between the horizontal plane, which we can say there's a horizontal plane here, but there's a whole series of horizontal planes, and that inclined plane. But we can get a strike line and an angle of dip.
The orientation of a plane is noted by recording the strike followed by the dip. There are 3 separate but similar conventions for doing this. All the following examples refer to the plane denoted by the strike and dip symbol shown here. One uses the bearing of the strike line, normally specifying the bearing in one of the northern quadrants. For example, north 45 east rather than south 45 west, followed by the value, for example 62, and the quadrant toward which the dip line is inclined, for example southeast or northwest if the strike is oriented northeast southwest. Thus, a complete reading would be written as north 45 east, 62 southeast for a plane inclined to the southeast at 62 degrees and striking north 45 east, south 45 west. The orientation of a plane is plotted on a map by drawing a line trending in the strike direction. A shorter line is then drawn in the direction of dip at 90 degrees to strike, and the dip angle is placed at the tip of the dip direction line.
Okay, what they've defined here is the quadrant method of reporting strike and dip. The quadrant method requires us to only use the north half of our compass. We never report strike using the south half of our compass. Remember that a strike line is a straight line. So anything we report up here, also we could technically report down here. But we, by convention, we use the north half of the compass. So in this example, this unit is striking north 45 degrees to the east. And that's how we would report. It's dipping to the southeast at 62 degrees. So by convention, we would write it in this manner: north 45 degrees east, 62 degrees southeast. That is the conventional quadrant method of reporting strike and dip. If you had taken this geology or structural geology when I took structural geology, this would have been the only method of reporting strike and dip that you would have learned. That's what everyone used.
The second convention essentially is the same, but replaces bearing with azimuth. Using the same plane as before, one would write 045, 62 southeast, or one could record 225, 62 southeast. The third convention, known as the right-hand rule, is similar to the second, but always records the azimuth of the strike line when the plane is dipping to the observer's right. In our example, this would result in a reading recorded as 045, 62. The advantage of this method is that only numbers need be used, which simplifies data entry if using computer analysis of orientation measurements.
Okay, we are going to use the quadrant method. I'm requiring you to understand the quadrant method of reporting strike and dip and the right-hand rule. Let's say, for example, using the right-hand rule, if I were standing at an outcrop and I was standing on the Earth's surface and I was looking to the northeast, my right arm, I could point in the direction in which the beds are dipping. So the right-hand rule, you'll always be looking down the strike line with the beds dipping off to your right. If I turn myself around and look this way, the bed would be dipping toward the left, my left hand. I'd have to flip myself around and look the other direction to report the strike. In this case, 045. Remember that we put the 0 in there so we can recognize that as a compass direction or a trend. And then the dip is 62 degrees. Once we have those two numbers, we can enter those numbers into a computer program and do a lot of mapping. Makes life much simpler. Now I'm going to tell you that I've age dated myself because these computer analyses did not really exist when I was doing structural geology and we were only reporting the quadrant method. Nobody cared if we had these azimuth numbers. Now, today, this would be the best way of reporting our structural data. And as we go through the class, we'll be using the right-hand rule more than the quadrant method, but you will need to learn both ways.
Be sure to remember that strike always precedes dip in orientation measurements. When using an azimuth convention, the first number, strike, should always include 3 digits, and second number, dip, only 2, thus 045, 62. Recall that when recording the orientation of a line, plunge is written before trend. Thus, for example, 62, 135 would refer to the orientation of the dip line using example plane. The above-mentioned approach is usually employed by North American geologists, but it's interesting to note that things are done a bit differently by European geologists. In Europe, a plane is defined by recording the plunge and bearing of the dip line. Planar data are plotted on a map in the normal method for lines, arrow oriented in the dip direction with dip placed at the tip of the arrow.
Again, the key here is being able to tell the difference between plunge and how it is reported and strike and how that is reported. If you didn't quite get that, play this through again, read it so that you understand how to report a strike and dip of a plane versus the trend and plunge or plunge and trend of a line.
Measure strike with a Brunton by placing the edge of the compass parallel to a strike line. The edge will be parallel to a strike line when the entire edge is in contact with the planar surface being measured and the compass is horizontal. The trend of the strike line is then read from the graduated circle. When using the right-hand rule, the compass must be oriented as shown here. The sighting arm is pointing parallel to the trend of the strike line when the plane is dipping to the observer's right.
So again, right-hand rule, this is our sighting arm. If this geologist stood up, their right arm would be pointing in the direction of dip.
Determining dip is the same as reading the plunge of a line. Simply align the side of the Brunton along the dip line, perpendicular to strike. Center the clinometer level and read the clinometer scale.
Again, this geologist is demonstrating the right-hand rule. They're looking in the direction of strike. The bed is dipping to their right.
The well-exposed surface of this sandstone layer provides a good location to measure the strike and dip of the sedimentary bedding. Note the yellow strike and dip symbol on the bedding surface in the photograph.
Again, if I were standing right here and looking in this direction, the bed would be dipping off to my right. Good example, the right-hand rule. So this is a strike and dip. We report the amount of dip as an angle at the end of the dip line.
Match the strike and dip notations and map symbols by dragging the correct notation and placing it in the brown box below the appropriate map symbol. After filling all 6 boxes, you may check if your answers are right.
Okay, you can't drag yourself, so I'll let you stare at this for a couple minutes and see if you can figure out which one goes to matches each symbol. Now, one of the tests here is that they have down here the azimuth method, which includes a direction of your dip, the quadrant method, which includes, the azimuth method, this one, which includes the direction of your dip, the quadrant method, which has your strike and dip, and right-hand rule. So we have to be careful which one we're putting in each of these diagrams. So the first one we would match using the azimuth method, 0, 50, 24 northwest. That's because we include, if we did the right-hand rule, we wouldn't have the northwest on here, and this number would change. Well, let's see if we got it right. All right. So again, if you're not sure where those came from, take a little bit of time, go back to it, look at it again, even write it down on a piece of paper and see if you can figure it out.
You already know about two special types of lines in a plane, the strike line and the dip line. Recall that the orientation of the strike line is denoted by its trend, bearing, or azimuth, and that the orientation of the dip line is defined by its plunge and direction of plunge. There exist many other possible lines in a plane, for example, current direction, fault, slip, that we eventually will need to deal with. We already know that any of these lines, such as the one in the diagram, are defined by plunge and trend. Many times it will be easier or more convenient, however, to measure the angle a line makes with the strike line in the plane it lies in, measured within the plane. This special angle is termed rake.
So what we have here is a plane. We have lines that are created within that plane, and we can measure that angle between our strike line and that plane. Basically, this is a protractor angle that we can make a measurement with, and we report that as the rake angle. It just defines the direction that line is going relative to your strike direction of your plane.
The rake of a line is defined by the acute angle the line makes with a strike line and the general compass direction toward which the line is inclined. For example, 30 northwest or 30 north. For any line, the orientation of the plane in which it lies and the rake angle and direction completely define the orientation of the line.
And this, again, this is just something in the field that a geologist would record if they recognized a consistent trend of a line that's been created within a plane by a variety of geological events.
These tool marks on the exposed surface provide current direction information. The current which formed them flowed parallel to the trend of the marks. It's straightforward to measure the strike and dip of the surface, the yellow lines, and the rake of the tool marks, the blue line, which fixes their orientation in space.
Okay, for those of you not familiar with a tool mark is, say this is the bottom of a stream bed. A tool mark would be created every time a stick was dragged along that bottom, leaving these now what appear to be ridges within the river bottom. So this bed then has been, which was originally horizontal, has been tilted at some angle. Therefore, it's coming up, it's no longer horizontal. So now it has a strike because it has a tilting plane that makes an intersection with the Earth's surface. So that's our strike line. And then we have dip direction, degrees to strike. And within that plane, that's been uh, impacted by structural event, plate tectonics, we can measure the angle of those tool marks. So this blue line runs parallel to those tool marks. And so the angle between the strike line and the tool marks is the rake. And again, that defines the location of those tool marks within this plane. And it's something, again, as structural geologists, we can report this, we can put this in our map, that another geologist can read and know exactly what is happening within that plane.
Check the box that specifies the correct value for the rake of the yellow line.
Okay, so the green is our strike line. So this is our dipping plane. This is a strike line. Let's for example, say this is a tool mark. And it crosses the strike line at some acute angle, an angle less than 90 degrees. Well, our choices for angles are 55 and 30. That looks probably closer to 55 degrees. The direction is toward north, so we'll choose 55 north. And is it right? All right. So again, take a look at that. Spend a little bit of time if you're not quite sure how I did that. Another example, north is going the other direction now. Again, a strike line. This is some line that's been created within that dipping plane. This is a larger angle than the 55 degrees that we saw before. But again, we're looking at the acute angle, not the obtuse angle. Make sure you don't get that confused. The acute angle. So the biggest angle we have here looks like 72 degrees, and it's toward the south. So I'm going to choose 72 south. All right. And one more. Again, here's our north arrow. This is our strike line. This is the line that's within the plane. Here's the acute angle. Acute angle looks like we have choice either of 10 degrees or 80 degrees. That looks like it's much more than 10, so it's probably at the 80 degrees. And it looks like it's heading toward the south based on our cardinal direction. So choose 8 degrees south. All right.
We now are at the end of the chapter. To review any section or chapter, click the main menu button. Important terminology discussed in this chapter includes azimuth, bearing, dip and dip line, inclination, plunge, rake, strike and strike line, and trend. If you are unclear about any of these terms, you may wish to consult the glossary. Otherwise, click the forward button to continue to the next topic, map interpretation, simple planar surfaces.
Okay, again, these are key terms that you need to learn. Write those down. They should also be in our lab. You can also, of course, look these up in any geology-related Google search. You can get a good idea. Also, YouTube is a good place sometimes to look to get examples of what these things are. So thank you. I hope this helps. Let me know if you have questions. Stay well.